So let me begin the session. Okay. 네, 안녕하세요. 저는 오늘 행사의 진행을 맡은 스페이스 레이더 대표 박시수입니다. 참석해주신 모든 분들께 감사 인사드립니다. Hi, I'm Park Shisu, CEO of Space Radar. I'm your host for today's workshop. I'd like to thank everyone for joining us today. 오늘 온라인 워크숍은 미국 우주기업 보이저 테크놀로지스가 추진하고 있는 민간 우주정거장 스타랩을 소개하는 자리입니다. 스타랩 프로젝트의 고객, 벤더, 전략적 파트너 또는 투자사로 참석을 원하는 분들께 유익한 정보를 제공하는 자리가 될 것입니다. 이를 위해 스타랩 프로젝트의 핵심 인사들이 현재 이 자리에 참석하고 있습니다. 곧 이분들의 발표가 있을 예정이고 여러분들의 질문에도 직접 답변을 해줄 예정입니다. Today's online workshop is an introduction to Starlab, the commercial space station being developed by the US space company Voyager Technologies. This workshop will provide valuable insight into the Starlab project, especially for those interested in joining the initiative as customers, vendor, strategic partners, or investors. To that end, I'm pleased to welcome key members of the Starlab team who will be presenting shortly and answering your questions. 워크숍은 90분간 영어로 진행될 예정입니다. 또한 오늘 워크숍은 녹화될 예정으로 행사가 종료된 후 스페이스 레이더 유튜브 채널을 통해 다시 올라갈 예정입니다. 워크숍을 다시 보시고 싶은 분들은 스페이스 레이더 유튜브 채널을 통해서도 다시 볼 수 있다는 점 명심해 주시면 좋겠습니다. The workshop will last for 90 minutes and all presentation will be conducted in English. Today's session will also be recorded and uploaded to the Space Radar YouTube channel after this event. If you'd like to revisit the workshop later, you can watch it again on Space Radar YouTube channel. 영어로 진행되기 때문에 발표되는 내용을 이해하기 어렵지 않을까 걱정하는 분들이 있을 것이라 생각을 합니다. 이런 분들을 위해 연사들은 천천히 그리고 정확한 발음으로 발표를 해주실 거고요. 또한 화면 하단에 현재 보시면 영어로 발표되는 내용을 한글로 실시간으로 자동 번역해주는 기능이 있습니다. 여기 하단에 보시면 그 캡션 자막 표현이라는 어떤 단추를 보실 수 있을 텐데요. 그것을 누르면 영어 발표가 실시간으로 한글로 번역되는 기능을 여러분들께서 보실 수 있으니까 필요한 분들은 사용하시기 바랍니다. Since the presentation will be in English, we understand that some attendees may be concerned about understanding the content. To assist with this, our speakers will speak slowly and clearly. And in addition to this, there is a feature that provides real-time Korean translation of the English presentation at the bottom of the screen. Please click the caption button at the bottom if you'd like to use this feature. 모든 발표가 끝난 후에는 여러분들의 질문에 대한 답을 하는 Q&A 세션이 준비되어 있습니다. 발표를 듣는 와중에 궁금한 점이 있으시면 여기 채팅방에 영어로 질문을 올려주시기 바랍니다. 모든 발표가 끝난 후에 질문에 대해서 관련된 분들께서 직접 답변을 하는 시간이 있겠습니다. After all presentations are complete, there will be a Q&A session. If you have any questions during the presentation, please post them in English in the chat box on the right side of your screen. We will address your questions at the end of all presentations. 그러면 첫 발표자를 모시도록 하겠습니다. 첫 발표자는 팀 커프라 스타랩 스페이스 CEO께서 스타랩 프로그램의 현황과 비전 등에 대해서 15분간 발표를 해주시겠습니다. And now, I'd like to welcome our first presenter, Tim Kopra, CEO of Starlab Space. Tim will give a 15-minute presentation on the current status and vision of the Starlab project. Tim, stage is yours.
Easy, Sue. I appreciate that. See the presentation coming up now. Maybe just to start with an introduction. Thank you for your interest in our space station, which is really a transformational way for us to work in low Earth orbit. I've been the CEO here for the past year and a half, and have to say that it's my favorite professional job that I've had within my career. I started out as a military aviator and test pilot, but also served as an astronaut for 18 years. Spent 8 months on board the International Space Station, was commander of the space station during my second mission. And since then, I've led space companies and have the privilege of leading an amazing team. One of the things that I thought about when I first left NASA was that if the United States and the international community ever built another space station, two things would make a tremendous improvement. One is we should make it much less complex, because the International Space Station, although a great achievement, was built one element at a time, and it took such a long period of time, over 11 years, to get to full assembly. So one thing I thought was, let's reduce the complexity. The second thing is the International Space Station is a collection of partners and their countries that have partnered together. And my thought was, we should do this with the best-in-class companies instead of countries. And so here we are today with those same sort of elements. One, a less complex but purpose-built space station. And then secondly, having built a really amazing joint venture. Next slide. And along those same lines, what we've built is this global venture, which we'll go through here in a moment, and then purpose-built as well. And we've also added artificial intelligence to the mix, because we're able to take advantage of advanced technology and make sure that we're very efficient in terms of how we operate this space station. Next slide. And this is a transition from government ownership to commercial ownership and using space stations as a service. NASA has done this before. When the International Space Station was retired, beforehand, NASA decided to start with two programs, a commercial resupply program and a commercial crew program. And this is important to NASA because it provided redundancy, it provided competition and pricing pressure. And so NASA is using a very similar process as we go forward in this next phase of human spaceflight. It's also a joint venture, as I mentioned, and we'll walk through the elements of our joint venture and why it's so important to both the business and the international community. And we're single launch to orbit, meaning that we don't have to assemble in space, and a very purpose-built space station, because we see the future not just taking advantage of the zero-G environment to meet the exploration objectives of countries around the world, but also this burgeoning space market, and with many proof points in terms of what we can do in that environment. Next slide. So even though the International Space Station is an amazing engineering achievement and has done tremendous amount of benefit from the standpoint of international relations, it's time to retire the ISS. It's been going around our planet every 90 minutes with a crew on board since 2000. So a permanent presence in space for the past 25 years. But NASA started planning to retire it back in 2021 when they established a program called Commercial Low Earth Orbit Destinations, where they selected, in that portion of the program, 3 competitors, ourselves, Northrop Grumman, and Orbital Reef, a combination of Blue Origin and Sierra Space. Northrop Grumman joined us, and so we're very grateful to the program to have $218 million funded from NASA in this first phase. If you look at the overall program today on the ISS, this international collaboration spends about $6 billion a year to maintain and operate the station. About $4.5 billion comes from NASA. And as part of this program, NASA wants to make sure that we're very efficient and save money for the government and also give the advantage to the commercial companies. And what we see is a station that not only is able to meet the exploration objectives of each one of the partners and the broader international community, but also focusing on the pharmaceutical companies, biotech, biology, chemistry, semiconductors, because there are unique aspects of the zero-G environment that you'll learn about today that is extremely beneficial, taking advantage of that zero-G environment. One of the other factors that's in consideration, and especially from the perspective of the United States, but I think it may be shared around the globe, is that the only other space station is the Tianyong station, which is similar to the International Space Station in that China has a continuous human presence in space and is advancing technologies. So there's actually an international competition with respect to making sure that the United States and our international partners can maintain the same level of research and beyond in low Earth orbit. Next slide. The international partnership that we've established as part of Starlab, we believe is very powerful. As I mentioned at the start, instead of partnering with countries, we partnered with the best-in-class companies within countries. Companies that not only have great flight heritage, but they also have strong relationships with the space agencies within their region or country. Voyager Technologies is an expert in all things that go on board the International Space Station with over 1,300 payloads that have been flown to the ISS. Has the Bishop Airlock on board space station today, has launched about 330 satellites. Palantir, as I think you know, is a world-class robotics company, and they've already demonstrated how they can create incredible efficiencies when it comes to our operations on board, especially when it comes to logistics, monitoring the experiments, crew time, and developing a digital twin that allows us to be very efficient with our maintenance. Airbus, we all know as an aircraft manufacturer, but they also built and maintain the Columbus module that's on board the space station that was installed back in 2008. Mitsubishi at large built 3 of the elements on board space station, along with the HTV transfer vehicle that brought supplies to the International Space Station. And MDA, which is a company in Canada where I led the robotics and space operations for a couple of years, has world-class robotics, built the Canadarm on the space shuttle, has Canadarm2 and all of the robotic systems on board the ISS, and now is building the Canadarm3 for Gateway, which is a space station that's also international and going around the moon. And what's also important is the relationships between those space agencies. What that means for us is that we have a very close collaboration with ESA, JAXA, the CSA, which is the Canadian Space Agency, along with NASA. And so by having that space flight heritage, what that means is that we can build a space station that is both commercial and safe and is tailor-made to work towards all of the experiments that are required to meet the exploration objectives on board space station. Next slide. So an overview of this space station. This is a single launch to orbit, meaning we don't have to assemble in space like the ISS or frankly some of the other people that were within the marketplace. And we're building this out of standard material. This is not an inflatable. We understand pressure vessels and we understand how to build the overall structure. And this is a massive space station, about 8 meters across, 3 stories tall, about 35% of the volume of the International Space Station, but also can conduct all of the research requirements for NASA, the international partners, and the commercial sector. Large windows, which are important for the crew. I can testify to that. We have the ability to expand, also receive visiting vehicles for cargo and for crew. And with the world-class robotics that come from MDA, that means that we don't have to be reliant on spacewalks for our maintenance. We've also ensured that it's purpose-built on the inside. One of the factors about the ISS that probably isn't that obvious is that because it's made up of a bunch of very small modules, it's not efficient from the standpoint of setting up the experiments for the crew. It's essentially a house in space that has many small rooms, whereas when you have a large structure like ours, you can organize your day in a very efficient fashion. And then this is a full-blown space station. It has power and propulsion to maintain its orbit and attitude. It has the ability to generate power to reject the thermal buildup on board the space station. And so we're very excited about the value proposition that we have with our station that will launch on Starship in mid-2029. Next slide. So I mentioned that Starlab is able to meet the requirements of the international community. There are many things that have to be learned as the different agencies, NASA, ESA, JAXA, and others go to Moon and Mars and beyond. But along with that is this burgeoning commercial market. There have been many proof points on board the International Space Station when it comes to applications on the commercial sector. But the ISS is a government facility and not designed for really developing the commercial market and scaling it. You know, some of the most interesting developments on board the ISS that we'll be able to take advantage of and expand upon are things like the billion-dollar cancer drug called Keytruda from the pharmaceutical company Merck. On board the International Space Station, they're able to develop the fundamental protein crystal in mass of this drug called Keytruda. And what that means is that in the future, in the pharmaceutical industry, the potential to change the delivery mechanism, the side effects, but also change the patent or extend the patent. And the pharmaceutical industry is a $1.1 trillion industry that puts 15% of its profits back into research and development every year. Companies on board the ISS have bioprinted body parts. There's a company, Redwire, that bioprinted a human knee meniscus and vascularized it. Lambda Vision on board the ISS today is bioprinting retinas. So pharmaceuticals and life sciences, extremely interesting ways in which we can develop that market. The same is true with the semiconductor industry, where we've identified the entire value chain and ecosystem, and there are elements within semiconductors where we can create much larger crystals that we believe will increase the processing power of semiconductors by an order of magnitude. And even within the consumer products, Procter & Gamble used the zero-G environment, for example, to understand how complex fluids mix with each other. And as a consequence, they developed a product called Tide Pods. So we're excited about all of these different industries that have direct applications in the zero-G environment. Next slide. So we're convinced that this single launch to orbit is exactly the way that space stations should be built. In fact, once we built the first space station, we've already seen demand signals to build a second, perhaps a third. And we'll be able to do this at about 2/3 the cost because the non-recurring engineering is complete, ground systems are in place, and understanding how to do assembly, integration, and test even that much more thoroughly. So we're excited about the future. We're excited that you've decided to join us today and learn more about this really amazing innovation and what is going to be the future of human spaceflight in low Earth orbit. Next slide. And here I'll transition the presentation to the team we have here today.
Thank you, Tim. So good morning to everybody on the call. Good evening to you for those that are stateside or elsewhere. Brad Henderson here. I'm the Chief Commercial Officer here at Starlab Space. As a Chief Commercial Officer, my main goal is to understand how to create a business that surrounds Starlab. We are very focused on really creating markets and a worldwide and global market, not only through Starlab, but through all of our partners and future customers as well. So today I'm going to talk a little bit about, how can you approach Starlab, how you can work with us, either as a payload developer, a customer, a user of Starlab, and the variety of ways and things we can do to connect you into the community. Next slide, please. So currently when ISS retires, we have one major problem. There's an entire market that utilizes the microgravity environment, ISS today, that has no destination or nowhere to go. So as Tim mentioned, the Commercial LEO Destination Program is there to provide that next step in space research, market development, and really turn over the commercial markets over to industrialization of low Earth orbit. And so what does that mean? As we look at the key for what a CLD needs to provide, like Starlab, we're really looking at ensuring that we have a continuity of full capability from the ISS era that seamlessly transitions over to the commercial era and starts to expand and grow that economy and those markets. Many of the markets you saw before were the terrestrial TAMs that really we look at and say, what are the key technologies that we want to continue in space? Many of those technologies have started on the ISS and would continue, and the capabilities that we'll provide will continue in the research and the applied research, as well as the production of those markets. Next slide, please. So as we think about it and how we visualize Starlab, so Starlab is much more than just a space station. The space station is a key aspect. It is the star laboratory in space. It is that lab that provides the means and access to do the research that you will see in future slides of a lot of the areas of why do we use microgravity. But to start off, we want to think about the entire ecosystem that utilizes space. And we need to start to think about how we answer a lot of the following questions, like what problems can be solved through microgravity? What expertise do we need to do and bring together? How do we pull together partnerships to find those new research mediums? And we think about these is, and then how do we actually formulate those partnerships along those contracts and find the correct funding and partnerships through agencies to actually go accomplish what we want to do. When we think about this, we think about the three major tiers that utilize space and microgravity. A lot of this starts out in the academic communities. This is very much out of the universities that think about basic research, basic science, and answer some of those fundamental key questions of what can be done for that new drug, that new therapy, that new gene study, that next crystal growth. Really what does those breakthrough do to find and cure the next, version of a cancer or MS or some of those types of things. And so a lot of that comes out, that kind of seeking mentality comes out of the university environment. A lot of times it comes out of smaller R&D startup type places that come up with a key and novel way to go do something and need to do it through microgravity on orbit. A lot of times then that builds into this applied research. And so what we're trying to do is starting to connect our university environment through what you'll see in the following slides is really connecting the university environment to the science parks and companies around the world, and then also try to provide that as a pathway for research to evolve into productionization, industrialization, IP generation that will sustain those companies, those exit strategies. But we're connecting that pipeline of capabilities up. So we're creating not only a space station, which is pretty exciting, but we're really thinking about creating an environment, a new economy. And when we say we want to, industrialize low Earth orbit or commercialize low Earth orbit. We are truly building that network. We're building the gateway through those partners and those agencies in these countries that have historically been working at it. And now we're expanding that and tying them together as well through our own networks and our own connectivity here. Next slide, please. So as we think about this global network, in this slide, we're just representing a lot of the areas we're currently located. So you saw a lot of our partners, Mitsubishi in Japan. We're also tied in with a variety of universities in Japan to include Tsukuba University. We're also tied into the iPark that is just south of Tokyo. In Europe, we're of course naturally partnered with Airbus, which is a very broad European company across Europe. We're tied in with the Zurich Innovation Park and Science Park. So we have partnerships there to help tie in research. We're tied in with a variety of universities, tying universities to these companies in Science Park to provide that basic to applied research, to exit strategies into productionization, either in space or terrestrially. And then of course, across the US, we're partnered with a variety of companies as well, Voyager Technologies, Palantir, as well as a variety of channel partners that are really thinking about how do they utilize or currently utilize microgravity today. A lot of those companies are already partners on ISS. They already send payloads and research up there. But as they look at that, they say, okay, how do we expand from when ISS goes away into the future together? So naturally, we're also looking at how do we expand? How do we expand into Korea? How do we build that bottoms up network and connections into the universities? How do we find new science and principal research? How do we tie in with the Korean Space Agency to really start to say, how can we make a Korean market that goes and buys or goes and through Starlab all the way, from space back to ground, right? It's connecting those ties of the space to ground loop and closing those pathways. So, and as we look at it, we're expanding around the world. We have MOUs with a variety of countries and exploring how do we partner with them to expand space further? How do we tie in to those regions for new science, new technology? And then how do we connect all of these things together? How do we provide a connectivity network to really build this out? And so if you can go to the next slide, we'll talk about the benefits of actually connecting all these things. And then, in the following slides, we'll think about how does it actually physically connect through the data networks itself. So first off, we're really understanding that the terrestrial space research network is paramount to growing the economy, right? And we see a variety of benefits of how these connect, but really it's about, the physical infrastructure, but really it's about collaboration. It's about building those relationships, building those partnerships, and creating the collaboration ability to share IP. Space access is hard. Finding professionals that are ability to transfer knowledge of research, of terrestrial research into space research is difficult. So by bringing those communities together through the universities, through the science parks, and through our implementation partner network, we provide that connectivity to have more of those breakthroughs and accelerate those breakthroughs over time. So we're constantly, expanding the access to facilities, even within Starlab itself. We understand that connectivity of understanding the telemetry, understanding the data that comes down, having real-time access to payloads both in space and terrestrially, so you can do analog experiments is important. So we're building up not only the physical infrastructure through science parks, payload research centers, and the like, but then connecting them into the Starlab ontology in our network, so then data can flow between two and they can flow directly to customers and user base home bases within the countries or within the companies where they can access their data, their payloads real time from Starlab, at the time of need. So you don't have to actually go to NASA. You don't have to go to the space agencies around the world to go get that connectivity. You can get it right where you're at. We've understood that the space environment has expanded so rapidly, right? We leverage the space every day, everything from GPS to satellite imagery to Google Maps, you name it, that data is right in your hand. We have to think, the next step of research in space should be able to get to the user directly. So we're really working on connecting all of those things together. So as we think about that, go to the next slide, please. We think about that physical connectivity, and these are some of the space services that we're starting to pull together and match up. A lot of these are still in work, right? The space station is still in development and the entire ecosystem is in development, but understanding the various hubs that we connect together, everything from what you see right in the middle, Starlab is the space laboratory. That has to have connectivity into our systems integration and ground labs. It's got to have direct connectivity into university research, direct connectivity into research data centers, and different pathways to get into and provide the data to where the work is actually being performed. We also see it being the direct connectivity into user home bases, UHBs, along with companies in the science park that are also conducting research and bringing these together. The loop that we have around is all the different networks that we're building out so customers can see and access their payloads in real time. Everything from research hubs where we're looking at connecting universities to corporate research to things and shared open source data that can be data mined to understand who's doing what around the world, who wants to access data, who wants to find partners. And so being able to enable the entire environment to build out those connections. To Customer 360, where folks can actually have access to, the payload planning platforms, the payload booking systems, those types of things that are all starting to come online over the next year, but really provide that ability and visual into the station where you can really see where my payload will be hosted, where, what flow and process flow it will go through. When will the astronaut touch the payload? All of those things you can actually access in real time through the data we have today. And a big part of that is connected through our Palantir partner, which is world-class AI, right? AI and efficiency optimization and building out this connectivity of all these different data hubs. Next slide, please. So for the purposes of today, I just wanted to kind of throw out there kind of what we see as far as our key customer and how to engage across the board. Really, as we think about Starlab, we think about the major customers that you see: Heritage, right? The government institutions, NASA, ESA, JAXA, KSA, you name it, that really are kind of the key tenets on the International Space Station that provide payloads and research and things of that nature. And we don't see that going away. We understand that we have to enable and work with these government institutions and continue the constant access for laboratory utilization in low Earth orbit. That's fundamental to how we think about our partners. But there's also a variety of ways to access us, to engage with us across the board. Everything from commercial implementation partners, those folks that truly understand and already do research in space. We can partner with them to continue their business. Their business is important to continue because they're that conduit from customers that may not use space regularly, with the knowledge that partners them up with us, and then they can execute on board on behalf of third-party clients. We think about channel partners. Channel partners are another way that we funnel through. Is they're more of the access, the education. They're really trying to drive clientele and new solutions to companies that really don't fully understand how to access microgravity, what it brings to them and their solutions, but they provide and actually help with those solutions. And then we also talk about, direct channel and commercial partners. And so these clients are very much direct into Starlab. They're saying, hey, we don't understand exactly what we need to do, so we want to come directly to Starlab, help us solve this problem. We want this outcome. We have our own chief scientist even on the phone today who can actually reach out and help understand what the problem is, where they want to go, find the right partners, and lead you guys to new and novel solutions in space. Please, next slide. So just kind of as a platform, as we wanted to put it here, is really to show what is available on Starlab at the very highest of levels. And we can get much more into detail as we go forward and as you engage with us over time. But as we think about it, there's two fundamentally kind of major infrastructure plans on Starlab itself. We have a base laboratory on orbit, which holds a lot of the basic functions you would find on ISS. Everything from glove box to incubators, freezers, fridges, and microscopes, centrifuges, things of that nature. We're planning on being able to have a hosted set of capability that is really focused on providing researchers on orbit with a laboratory-like environment. Think of it as almost like a commercial research organization on orbit that you can access through data. You can send up payloads, you can send up reagents and other materials, things of that nature, and access and utilize that lab on a pay-by-play basis. And then we think about that as also on the right side is thinking about it as a lease space, right? If customers are interested in coming up and renting volume, we're already taking pre-booking orders and filling up. But if people are interested in really understanding and kind of renting or owning space on Starlab for continual research and then build their business through that, and then we are just the access and infrastructure to host your payload platform or payload facility, that's another way that you can access Starlab overall. Next slide, please. Alrighty, so I'm going to go ahead and introduce our chief scientist, Luis Zia. So Luis and I go back for multiple years, and so good to see Luis. And he's going to talk today about why microgravity and what we can do there.
Wonderful. Thank you, Brett. And it's a pleasure to be here. And I'll echo the thank you to everybody who joined the call. If I can have the next slide, please. I'm going to try to compress a 5-month-long space life sciences graduate course into the next 14 minutes and 40 seconds. And I will supplement that with a little information on how microgravity can also help us with physical and material sciences. And I'll start that by going into the past, actually 3,500 million years into the past. And that's when life started on Earth. It has been evolving since to a changing world, changing in terms of the constituents in the atmosphere, the salinity and the pH of the ocean, the temperature. Next slide, please. But there has been one thing constant, and that is gravity. But now we have the ability to treat gravity as an independent variable, meaning that it's something that we can change and then see what the effects of that change are in cells, tissues, and organisms. Next slide, please. And this has the potential to unmask molecular and biological processes otherwise unexplored on Earth. So next slide, please. What I'm going to do here is I'm going to give you a few explanations of why microgravity is used currently or how it can be used in the future to enable improvements in processes, may them be purely scientific or actually industrial, because it's already well known what it is that it can produce. And I'm going to do it in a narrative fashion. I'm going to try to tell you small stories, short stories that speak of specific examples to each of the points that I'm going to say here. I've been very fortunate of working on 26 experiments performed in space, both as an aerospace engineer as well as a scientist. And I'm going to start with one that is dear to my heart because it was my PhD thesis performed on the International Space Station. Next slide, please. And here where I'm going to show you is pictures of E. coli. E. coli is the bacteria that sometimes makes the news when there are outbreaks and infections. On the left is a picture taken of E. coli grown on Earth, and on the right is in space. But also, besides the gravitational environment, the other change is the amount of the concentration of antibiotic that E. coli was challenged with. In space, we have a higher concentration because bacteria on Earth under those concentrations of antibiotics just could not grow. It was too much. So we call that an inhibitory concentration of antibiotics. And in space, it behaved differently. And actually, the reason for which I got into science from aerospace engineering is because I almost became part of a statistic of hundreds of thousands of people who die every year from bacterial infections that we can no longer cure with antibiotics. I went scuba diving. I used to live in Florida. I got an ear infection that became a throat infection. I got the wrong doses of antibiotics that cleansed my intestine to the point that only drug-resistant bacteria were living in certain parts of my intestine. They were going to remove it. If they couldn't remove it, that I could be part of that statistic. Fortunately, they were able to fix it, but I know a lot of people don't have that story. And next slide, please. This is a perfect example of how microgravity can unmask these processes. I'm going to show you three things that seem rather complex, but they're actually simple when you think about them. Bacteria, specifically E. coli, has a set of genes called the entericidin locus. Here it's a box that you see as ECNAB. Well, one of those genes tells the bacteria to kill itself, basically, to burst its membrane. And we hypothesize that bacteria do that to increase the probability of survival of the whole colony when they are under certain types of stress. So people ask themselves, why don't we make a new class of antibiotic that triggers that gene that makes the bacteria kill itself? And that gene is called RPOS, which is the box to the left. Nobody wants to touch that one in the case of E. coli, because if you were to turn that switch would not only turn the light of the gene that makes the bacteria kill itself, it would turn 156 other lights, 156 other genes, most of them making that bacteria even worse. But in microgravity, what we saw is that the enterocytin locus, that gene that made the bacteria kill itself, under certain conditions where it was turned on over 24-fold with respect to the same conditions on Earth. And more interestingly, the RPOS switch was not flipped. So then this enables us to generate a new hypothesis that there may be an alternative switch to this suicide gene in E. coli that can be the target for antibiotics. Next slide please. So that is one of the reasons. The other one is that microgravity can have deleterious or negative effects on human health that are or mimic an accelerated disease model. And here's the second story I'm going to tell you. Next slide, please. And also, just to make this more relatable, my mom, for example, she's one of 7.5 million patients who take this medicine called Prolia from Amgen. This is a medicine against osteoporosis, the worst type of untreated postmenopausal osteoporosis on Earth. Can translate to about 1.5% bone mass loss per year. Now, if you're in space, you can have a higher percentage of bone loss on weight-bearing bones per month. Now, this is a problem, as we want to make sure that humans are able to explore the solar system and beyond in a healthy fashion, but it also serves as an accelerated disease model where companies can test molecules. That's what Amgen did on the STS-108 flight. And basically, a cohort of mice were flown to space. Another one stayed on the ground. Half of the mice in space got the molecule. The other half got the placebo. The mice that went to space and got the molecule, they had more bone than the ones that were in space but had the placebo. And they even had more bone mass in some cases than the mice that stayed on Earth with the placebo. Eventually, this molecule became denosumab and Prolia, which first and foremost, it helps millions of people on Earth yearly, including my mom, as I mentioned. But for that company, it's a $2.7 thousand million of yearly sales. Next, please. Microgravity can also suppress forces, specifically buoyancy, sedimentation, and convection. So if you think of the equations for these three, they all have a G multiplying a whole thing, and that G is gravity. Now, if you make that G very close to zero, the whole thing goes to zero. Next slide, please. And that can help in several ways. It can help from the micro level all the way to the macro level. Next slide, please. And what we're going to focus on is on the micro. So why does that matter? So the fact that you can turn off basically buoyancy, sedimentation, and convection allows for other parameters such as Brownian motion, which is diffusion, superficial tension, conduction, capillary flow, and other types of forces to govern processes. Next slide, please. So as I mentioned, we're going to focus on the left side first, where you see there's a little image of proteins finding each other in a medium. And when they do, they start growing a crystal. And on Earth, in this image, which is a snapshot from an image from a video from NASA, you can find as described below. The yellow proteins are describing proteins that did not bind to the crystal in the right fashion. And this is because you have flows in the medium, you have all these forces that we were talking about. Next slide, please. But in space, you don't have those. So you have better organized proteins. On the bottom right, you see an image of these are monoclonal antibodies, a type of protein. The image on Earth, and you can see how they tend to cluster, to clump. And on the right, you can see a more homogeneous distribution of also a more close homogeneous size of this protein. Really, this is why this matters, and I'll give you the specific example. And this is something that Tim mentioned. Merck has this drug, actually it's its bestseller. It's 40% of Merck's revenue comes from this drug called Keytruda that helps a lot of people, hundreds of thousands of people with cancer. So they had this monoclonal antibody already figured out. It was a medicine. It already being used on in clinics and with doctors and patients. But by nature of flying into space, they were able to allow those proteins to form those more better structured crystals, that then when you have a larger crystal, what you can do is you can understand its structure better. You put it under, for example, Raman spectroscopy or other type of analyses, and you can understand the structure of the protein. That matters because if you understand the structure of the protein, you can understand its function. And basically, most diseases are related to a protein one way or the other, either because the origin of the disease is a protein that is not properly folded, it was not properly synthesized, it's not doing what it should be doing, or because the medicine itself is another protein that needs to bind with it, like two very unique sets of Lego pieces that need to find how to match exactly. And that's why it's so important to understand the structure. Well, by flying into space once, this is important to mention that it's not that they needed to have a factory in space. They only had to fly it once to understand the structure better. With that, they were able to reformulate it, which translated in these three sub-bullets that you see here. First is that they had improvements on the manufacture. So it was simpler process to purify it. They had improvements on the storage. That means that if you are a clinic in a rural area in a developing country, for example, where there's very little access to -80 freezers or even to -20 freezers, then this helps people. This helps people because more people can have access to these medicines. And importantly, for the patients, the delivery process changed from being sitting down for hours and coming back every other time to get the intravenous delivery. Now it's a subcutaneous injection, like if you're getting a shot for a vaccine, for example. Importantly, again, the hundreds of people that are positively impacted from this. And from Merck's perspective, from the ROI, not only did they lower cost in manufacture, storage, and delivery, but they were able to reformulate it, which translated with an extension of the patent. And if you're a company where you're about to lose part of your, 40% of your revenue because your bestseller, you're going to lose the patent, and you're able to extend it, that's a really big deal. Next slide, please. Microgravity can also help you construct large three-dimensional cellular structures, which can serve as better targets for drug discovery and development. The image you see here in the bottom is a picture I took of, this is lung cancer cells from a 26-year-old male. And what you see there is when you have cancer cells on the microscope, you're going to have them on focus here. So every little bubble that you see there, that's a cell. But as soon as you go in or like down or up on the microscope, you lose everything from focus because the cells just sediment to the bottom of the medium they're in. And then they cannot grow three-dimensionally because it's like if you were trying to build a three-dimensional structure with bowling balls. The weight of the balls will make them sediment to the bottom. Now, you don't have that problem in space. So in this case, for example, we were able to grow very large three-dimensional structures that would serve as targets for molecules that biotech companies are looking to see either the toxicity, for example, if those are healthy cells, or their efficacy in actually killing the cancer cells, or both. So if you have a incorrect target in terms of its form, its shape, its morphology, then you can have false positives or false negatives, which translate to it can translate to hundreds of millions of dollars and years of work that go to waste. Next slide, please. And there are others. So microgravity can also help for production of unique alloys and compositions. Next slide, please. For eliminating voids and ensuring continuous contact between the similar materials. Next. And for quiescent environments that may remove or minimize defects. Here I'll give you a few examples. If we can go to the next slide, please, Manuel. So these are some potential areas for how microgravity can help with advanced materials. So semiconductors, exotic glasses and fibers, metal organic frameworks, metamaterials, superalloy casting, and ceramics. Next slide, please. And in terms of semiconductors, there's been 228 experiments performed on the space station in terms of crystallizing inorganic materials with that focus that have translated to 151 peer-reviewed publications. And over 70% of those studies have found that in space and with respect to Earth, they have had bigger growth, better structure, and or better uniformity. Next slide, please. And I'll bring it back to Tim's slide of he mentioned here several markets. I just mentioned a few of them. As you can see, I didn't address them all. We didn't talk about agriculture, about stem cells. The point here is that there is a lot of a potential that microgravity can help with different processes, different industries. It can help people on Earth, and I think this is very important. One thing that is better than helping people on Earth is helping people on Earth in a financially sustainable way, where you don't depend on donations or something. So this is microgravity is an example where we can actually go do good for people and as well have return on investment for companies. Next slide, please. And I'll just finish bringing this back up to what Tim and Brad said. That is why we're doing Starlab. It's not only for the folks who are in the countries that build the space station, as the space station it tends to be. What we're trying to do here is open the door for scientists, entrepreneurs, students to be able to use microgravity as that independent variable that now, after 3,500 million years in history of evolution of life, we can do now. Thank you. And I think, Manuel, I don't know if you were introducing the next person, or I may introduce soon.
Thanks, Luis. I think I can take care of from now.
Thank you, Harrison.
Okay. All right. So I will share my slide. Just a minute. Hi everyone. Can you see my slide?
We can.
So which slide? Is a presentation view or just the regular slide?
This is the right view. You're good.
That's good?
Yes.
Okay.
Yes.
Yeah, so thanks to allowing me to give this presentation, also allowing me to present in Korean. So from now on, I'm gonna give my presentation in Korean. 안녕하세요. 예, 저는 오늘 이 보이저의 협력 파트너로서 이 오늘 워크숍에 참여를 요청받은 스페이스린텍 대표 윤학수입니다. 예, 그래서 오늘 제가 이 자리를 통해서 드릴 프레젠테이션은 오늘 저희 소개, 저 회사에 대한 소개, 그리고 저희 회사가 어떻게 보이저 테크놀로지와 함께 협력을 하게 되는지를 설명드리고 이러한 협력 관계가 왜 한국의 우주에서의 연구 활동과 산업 성장에 어떻게 중요한지 말씀을 드리도록 하겠습니다. 참고로 화면에 보시는 저희 회사 이름은 스페이스린텍이고 아래 보시면은 Life in Innovation through Space Technology를 보실 수 있을 텐데 이 의미는 우주 기술을 활용하여 삶의 혁신을 이루자는 의미가 있습니다. 저희 회사는 2021년 6월 16일에 창립을 하였고 저 포함 현재 19명의 임직원이 우주의학 연구 및 제약 생산 플랫폼 개발 및 서비스 사업을 위해 매진하고 있습니다. 현 임직원은 공학, 생명공학, 의학, 약학 출신의 10명의 박사, 그리고 4명의 석사 출신, 그리고 경영지원 인력 5명으로 구성되어 있습니다. 현재 우주 바이오 그리고 우주 제조 분야에 있어서는 보시는 슬라이드와 같이 많은 기업들과 연구기관들이 포진하고 있습니다. 미국의 우주 산업 컨설팅 업체인 스페이스 임펄스에서 제공한 자료를 보면 우주 산업의 제조, 푸드, 우주의학 분야에 오른쪽에 보시듯이 스페이스X, 노스롭 그룹만, 엑시엄, 그리고 여기에 보이저 테크놀로지 등 다양한 우주 기업, 그리고 일라이릴리, 머크 등과 같은 글로벌 제약 회사들이 이런 산업군에 포진을 하고 있습니다. 저희 스페이스린텍은 이 보시는 것 같이 드러그 R&D 및 제조 분야의 주요 플레이어로 분류되고 있고 우주의학 분야의 주요 혁신적인 기술 개발을 이뤄내기 위해서 지금 노력하고 있습니다. 잠시 저에 대해서 궁금해하실 수 있을 텐데 저희 잠시 설명을 드리면은 저는 미국에서 노폭 주립대 정교수로 재직하고 있고 하버드 의대 개공 교수로도 활동을 하였었습니다. 그리고 2010년부터 그 미국 나사의 연구 과제를 수행을 했었고, 그 미국에서의 의학 결과들을, 연구 결과들을 그 상업화하는 그 NIH의 그 연구 과제들을 심사하는 심사위원으로도 활동을 하였습니다. 그리고 이를 통해서 그 우주의학 분야에 대한 사업을 준비해 왔고 창업을 하게 되었습니다. 저희 이러한 그 독특한 이력은 그 지금과 같이 한국과 미국의 우주산업 협력 논의에 참여를 할 수 있는 바탕이 되었고, 실은 하나의 사례로 어제 워싱턴 DC에서 진행된 한미 우주협력 사업 워크숍에도 참석을 하였었습니다. 그리고 저희 회사 주요 인력 그 구성원들에 대해서 설명을 드리는 게 맞겠고요. 그 지금 보시는 왼쪽에 보시는 심정욱 CTO는 영국 리즈 대학의 교수로서 우주의학 시스템의 소용의 근간이 되는 그 마이크로 플루이딕스 기술의 전문가입니다. 미국 하버드 그리고 영국 캠브리지 대에서 오랜 수련을 받았고, 그리고 그 오른쪽에 삼성 SD에서 오랜 기간 PM으로 근무했던 그 김병훈 상무가 그 우주 플랫폼 개발 본부장을 맡고 있습니다. 그리고 그 오른쪽에 김병호 이사는 중해지역에서 그 신약개발센터장을 역임을 했었고, 이영훈 연구소장하고 우주 신약개발을 추진하고 있습니다. 그리고 그 오른쪽에 보시는 최학수 교수님 하버드 의대, 그리고 손문승 교수인 여주대 아주대 병원의 손문승 교수님께서 저희 우주의학 연구 신약개발 사업을 하는데 많은 도움을 주고 계십니다. 저희가 그 지금까지 이룬 몇 가지 주요 이력에 대해서 잠시 설명을 드리면서 저희 회사를 소개를 하도록 하겠습니다. 먼저 그 저희 회사는 그 대학병원 그리고 주요 연구기관에도 선정되기 어렵다는 한국형 알파H 프로젝트의 주관 기업으로 선정이 되었습니다. 그리고 그 국내에서 유일하게 지금 현재 우주정거장에 그 올 8월에 그 단백질 결정 성장 실험을 하기 위해서 스페이스X의 펠콘 9을 타고 우주정거장으로 이송을 시켜서 우주의학 실증 연구를 진행할 예정에 있습니다. 그리고 또 누리호 4차, 5차 발사의 그 탑재체로 그 선정이 되어서 향후 그 위성을 활용한 우주의학 실증을 준비하고 있습니다. 그리고 오늘 그 워크숍을 주관하고 있는 그 보이저 테크놀로지와의 협력을 통해 국내에서 최초로 우주정거장의 실험, 아까 말씀드렸지 예정이 돼 있고, 그리고 올 가을에는 그 미국 오하이오주에 조성이 되고 있는 그 우주기업 인큐베이터 클러스터인 사이언스 팍에 입주를 예정하고 있습니다. 그 보신 슬라이드는 그 저희의 그 핵심 사업 세 가지를 그 설명하고 있습니다. 먼저 아까 잠시 그 루이의 그 슬라이드에서 잠시 소개가 됐지만은 그 단백질 결정 성장이 지상에서는 아주 다르게 이루어집니다. 그래서 그 보시는 바와 같이 그 이러한 단백질 결정 성장 그 연구를 저희가 그 진행을 하고 있고요. 그다음에 두 번째는 그 단백질 의약품만이 아닌 원료 의약품 그 저희가 액티브 파마스티컬 인그리디언트라는 API 그 원료약품 생산에도 미세중력 연구를 활용하여 그 앞으로 신약 개발에 활용하기 위해서 노력을 하고 있습니다. 그리고 세 번째로 그 세포 치료제 개발 연구를 진행하고 있는데 그 세포 치료제 그 시장 자체가 2033년에는 약 54조 원 정도까지 성장할 것으로 전망되고 있고, 이러한 중력 환경 변화가 가져다 줄 수 있는 그런 많은 장점들이 있기 때문에 현재 이와 관련한 연구를 진행을 하고 있습니다. 조금만 더 설명을 드리면은 그 아까 잠시 그 루이의 슬라이드에서도 보였지만은 그 지상에서 이런 불균일하게 커가는 그 결정 성장이 그 우주에서는 이렇게 균일하게 성장이 됩니다. 이러한 부분은 그 단백질 의약품이 고순도 고균질로 그 제조될 수 있게 해주는데, 이러한 그 장점에 따라서 그 약물의 보관 수명 그리고 품질이 향상이 되고, 그리고 아까 잠시 설명이 되었지만은 정맥 주사가 아닌 피하 주사가 가능하도록 그 제형 변경이 되기 때문에 이러한 그 투약 경로 그 변경으로 인해서 환자의 편의성을 크게 증가시킬 수 있습니다. 그럼으로써 효과적인 환자 치료를 도모할 수 있게 됩니다. 이러한 그 우주에서의 신약 개발 및 생산들의 이점을 현실화하기 위해서 저희 회사 스페이스린텍은 그 그라운드 밸리데이션, 그 저희가 드랍타워를 사용을 하고 있고요. 그래서 그 그라운드 밸리데이션 과정을 통해 기술의 완성도를 높이고 그리고 우주에서의 그 실증 과정을 거쳐 우주에서의 CRO 그리고 우주에서의 CDMO 사업을 성공시켜 가려고 하고 있습니다. 그리고 이러한 사업은 오른쪽에 보시는 발사 일정을 통해 그 우주정거장과 인공위성을 활용하여 기술 개발과 실증을 진행할 예정입니다. 잠시 설명드리면은 그 먼저 2025년 8월에 아까 말씀드렸지만은 스페이스 팰컨 9을 타고 스페이스X 33, SBS 33 CRS 미션에 저희 시스템을 탑재시켜서 우주정거장에서 실험과 실증 과정을 진행할 예정에 있습니다. 그리고 2025년에는 11월에 예정된 누리호 4차 발사, 그리고 2026년 1월에 예정된 또 다른 그 CRS 미션 NG23 미션을 통해서 이 두 번째로 우주정거장에서의 실증을 진행할 예정입니다. 그리고 2026년 8월에는 그 누리호 5차 발사에 포함되어서 또한 저희가 원하는 우주의학 기술 개발의 성과를 만들어낼 것입니다. 그리고 그 이러한 기술 개발을 통해서 그 다음과 같은 수익 창출 구조를 만들어 나가게 될 건데 먼저 2025년, 2026년에는 단백질 의약품 결정화 모듈 실증 연구를 완수하고 지상 플랫폼과의 통합적 운영 능력을 확보해 나갈 것입니다. 그리고 2026년 하반기부터 2027년 하반기까지 저희 저궤도 플랫폼 실증 및 상업적 확장성을 입증해 갈 것이고 2028년, 2029년에는 저궤도 바이오 연구 서비스 및 CDMO 서비스를 확장할 것이고 2029년, 2032년에는 우주 환경을 활용한 바이오 연구 상업화 부문을 그 글로벌 시장으로 확장해 나갈 것입니다. 그리고 지금까지 자료를 통해서 짧게 설명드렸듯이 그 저희 스페이스린텍은 그 지상의 드랍타워를 활용하여 우주 의학 연구 및 생산 플랫폼 개발의 비용 및 시간을 크게 감소시킬 것이고 성공률과 신뢰성을 크게 높이며 사업을 이루어 나갈 것입니다. 한 가지 중요한 점은 이러한 우주의학 연구 개발과 생산 과정은 보시는 바와 같이 국내외 주요 네트워크를 통하여 진행될 것입니다. 이러한 네트워크의 중요한 한 축을 그 보이저 테크놀로지가 담당하고 있고 향후 스타랩, 지금까지 계속 말씀드려왔던 그 상업용 우주정거장 스타랩이 저희 회사 사업의 중요한 근간이 될 것입니다. 그리고 잠시 그 지금까지 이온 보이저와의 파트너십을 보여주는 사진들을 잠시 그 워크숍에 참여하신 그분들께 공유를 잠시 드리겠습니다. 이 사진은 제가 처음 텍사스주 휴스턴에 위치한 보이저 테크놀로지를 방문했을 때 사진입니다. 그리고 그 이후에 많은 회의들, 미팅들, 그리고 그런 상호 방문들이 이루어지고 있는데 그 사진들의 일부를 잠시 공유드리도록 하겠습니다. 이거는 그 저기 제프가 저희 회사를 방문했을 때 그 사진들이고요. 그 저희 직원들이 저희가 하고 있는 연구들을 설명하는 모습들입니다. 그리고 이건 저희가 거꾸로 그 보이저를 방문했을 때 그 저희 엔지니어들이 가서 엔지니어링 샘플들을 테스트하고 그리고 협력 결과들을 실은 이와 같은 그 모듈들로 그 나타나게 되는데요. 그 여기 보시게 되면은 요런 그 플랫폼 장치들이 지금까지 많은 미팅들 그리고 그 상호 간의 그 의견 교환을 통해서 이런 그 모듈을 만들어낸 것인데 향후 이러한 그 플랫폼 장치들을 우주에서 보이저를 통해서 그 우주 정거장에 올려서 실증을 하게 될 것입니다. 그리고 이러한 그 협력 과정은 앞으로 좀 더욱 강화시켜 나갈 것이고 그러한 부분들을 위해서 저희 회사는 아까 잠시 말씀드렸지만은 올해 가을에 미국 오하이오 주립대에 위치한 조지 워싱턴 사이언스 파크라고 하는데요. 이게 그 인큐베이터 프로그램입니다. 그래서 이 인큐베이터 프로그램에 참여하여서 상업용 우주정거장 향후 상업용 우주정거장 스타랩에서 진행하게 될 우주의학, 우주제약 연구 및 생산기술 개발과 그러한 그 장치들을 개발하는 것을 완성시켜 나갈 것입니다. 그리고 잠시 아까 뭐 저기 얘기가 됐지만은 왜 상업용 우주정거장이 중요한지를 잠시 한 번 더 말씀을 드리도록 하겠습니다. 먼저 그 왼쪽에 보이는 그 차트는 그 우주정거장에서 현재 우주 선진국들이 어떤 연구를 진행하고 있는지를 보여줍니다. 보시는 바와 같이 절반 이상의 연구들이 그 바이오 의학 관련 연구입니다. 이러한 연구 활동 중 민간 제약 회사들이 많은 부분을 지금 담당해 가고 있는데요. 그거는 오른쪽을 통해서 보실 수 있습니다. 보시는 바와 같이 그 글로벌 제약 회사 그 아까 머크, 키트루다 1년에 약 40조 정도의 매출을 발생하는 단일 품목으로 블록버스터 항암제인 키트루다를 우주정거장에서 제조하는 연구를 2017년에 시작을 해서 2019년에 완성을 하였습니다. 그리고 그 실은 그 작년 8월에 이 연구가 그 임상 3상까지의 실험을 마치고 지금 그 밖으로 출시될 수 있는 준비를 마친 상태입니다. 그리고 그 머크사 이외에도 여러분들이 잘 아시는 아스트라제네카 그리고 브리스톨 스킵 등이 그 연구를 심혈관 질환 그리고 단백질 기반의 바이오의약품 생산 연구로 그런 성과들을 내고 있고요. 그리고 그 오른쪽에 보이는 일라일릴리 글로벌 시총 지금 현재 1위죠. 그 일라일릴리는 당뇨병 질환 치료제 연구를 지금 진행을 하고 있습니다. 이러한 그 우주정거장에서의 연구 개발이 향후 그 우주 민간 시장에 그 많은 기회를 가져다 줄 텐데 먼저 그 최근 발간된 그 맥킨지 보고서에 따르면 우주에서의 의약품 산업이 단기간에 28억에서 42억 달러의 시장을 만들어낼 것으로 예상을 하고 있습니다. 그리고 그 이러한 그 우주 제조 민간 산업 성장은 우주 의학뿐만이 아니라 다양한 소재 개발 그리고 우주 반도체로도 빠르게 확장되어 갈 것으로 예측되고 있습니다. 그리고 이러한 우주 제조 산업 성장에 그 우주 정거장은 실은 지금보다 더 큰 역할을 할 것이고 오늘 이 워크숍을 개최한 스타랩은 그중 가장 중요한 역할을 맡아갈 것이라고 저는 생각하고 있습니다. 그리고 이러한 스타랩과의 파트너십은 우주 기술 개발과 산업 성장 부분에만 한정되지는 않습니다. 그리고 잠시 설명을 드리면 그 저희 회사는 강원도 지역의 지역아동 센터와 협력하여 온라인 우주 교육을 지금 2022년부터 진행을 하고 있습니다. 약 200명이 넘는 강원 지역 아동들에게 8주간에 걸친 교육을 그 스페이스, 그래비티, 라이프라는 주제로 진행을 하고 있습니다. 그리고 매년 스페이스 드리머 캠프를 통해서 우주 환경 및 과학 기술에 대해 공부를 할 수 있는 기회를 제공하고 있고, 그리고 사진에서 보는 바와 같이 그 나사 연구자들 및 우주과학 분야 책임자들을 초청하여서 이런 아동들이 미래 세계에서 어떤 역할을 할 수 있는지 커리어 멘토링 기회를 제공하고 있습니다. 지금 보시는 사진은 작년 9월에 한국을 방문한 나사 휴먼 리서치 프로그램의 디렉터인 데이빗 바우만 그리고 어소시에이트 칩 사이언티스트였던 맥피 젠시 등이 이 강원도 지역의 그 지역아동 센터 어린이들과 만나서 대화를 나누었을 때 찍은 사진을 보여주고 있습니다. 저희는 이런 미래 세대의 교육을 보이저 테크놀로지와 함께하고 향후 이 아이들이 만들어내는 디자인 그리고 장치들이 스타랩에서 실험되고 그 결과들을 이 아이들이 볼 수 있도록 할 것입니다. 그래서 이 아이들이 향후 우주 기술 혁신을 이루어내는 미래 인재로서 성장하는 데 도움을 주도록 할 것입니다. 예, 이것으로 제 발표를 마치겠습니다. 지금까지 경청해 주셔서 감사드립니다. 감사합니다.
Thank you very much, Hargsoon.
Thank you.
Next, we'll be bringing on Adi, who's the Senior Vice President of Corporate Development at Starlab, and he'll get to speak a little bit about not just how Starlab is a great scientific and engineering endeavor, but also a great financial opportunity.
Thank you, Manuel. Will you be able to pull a slide on the screen?
Does that work?
Yes, thank you. It's a pleasure and an honor to meet all of you. I am the Senior Vice President of Business Development at Voyager. Voyager is the majority shareholder of the Starlab joint venture, along with Airbus, Mitsubishi, Palantir, and MDA. Starlab provides an investment opportunity for qualified investors. Starlab should be viewed as an infrastructure-like investment, which means there is an upfront capital investment for a certain period of time, and that followed by a long period of profit generation over the life of the space station. What is unique about Starlab is that our capital needs are offset by government funding that include NASA and additional international governments, as well as customers pre-buy, and that reduces the need for Starlab to raise external capital and protect investors with less dilution. So we currently opened our first ever capital raise, Series C preferred shares, and qualified investors that would like additional information, please reach out to us and we can start the process. With that, I'm going to pass it to Jeffrey.
Thank you, Dee. And I'm going to pass it then to Sisu Park, who will lead our question and answers before I wrap up the evening or the morning for you. So Sisu, would you mind leading the question and answers?
Okay, sure. 질문 두 개가 지금까지 보내주셨고요. 뭐 더 궁금하신 게 있으면 지금 올리시면 제가 바로바로 추가를 하도록 하겠습니다. 첫 번째 질문은 so far we have two questions. I will read the question in Korean first, and then English, and then people who are appropriate to answer the question will just come up and then answer the question. 첫 번째 질문은 국제 우주정거장에서 피하에 투여하는 항체 치료제를 생산하는 임상 실험이 진행되었다는 보도를 접했습니다. 이 이니셔티브를 주도한 제약회사와 대략 몇 명의 환자가 임상 실험에 참여했는지 알고 싶습니다. I came across a report indicating that a clinical trial was conducted involving the production of antibody therapeutic on the ISS, administered subcutaneously. Would you happen to know which pharmaceutical company led this initiative and approximately how many patients were involved in this trial?
I think I can help with this one, Sisu. Thank you very much. Manuel, would you mind going to slide 31, please? So this is the example that I mentioned in the protein crystallization short story that I was mentioning. It was Keytruda. There's different metrics. There's different organizations that have come up with numbers to determine how long it takes and how expensive it is to go from a promising molecule to a drug, a medicine on the market. But one I like, because I think it's an average of averages, is $1,200 million and over 10 years to go from a molecule to a medicine on the market. So that is a very complex process, as you can imagine. Microgravity is not a magic wand that will help all problems, all challenges, but it is a piece of the puzzle that can help accelerate, can help reduce those 10 years to something shorter, and therefore the cost of going from molecule to drug on the market, if you can demonstrate that it works under conditions that are even worse than the worst type of scenario you could see on Earth. In the example, for example, of osteoporosis, that is also true for different cardiomyopathies, different diseases of the heart, muscle dystrophies, etc. So in terms of your question of going back to Keytruda, how many people were involved in the clinical trial, this is separate from the clinical trial. This is what microgravity enabled was understanding the structure of the protein better. As you can see in the top right, you see a bimodal distribution. So this is the two little humps like a camel. That is how when they try to crystallize this on Earth, it would look like. And on the right, you can see a mono distribution, a single distribution. This is the terms of diameter, which helps you have a more homogeneous solution that in turn enables the three sub-bullets here that we're talking about, for specifically that now you can go to a subcutaneous injection. So once they were able to do this, really several things happened. Now, so that they don't have to fly every time to space to produce this improved structure, now that you understand really what is the right size that you need it at, you can use devices on Earth. There's different names, rotating wall vessels, clinostats, etc., where you can simulate, you can replicate certain aspects that you see in microgravity, but you are not turning gravity off. You cannot do that on Earth. But just by being able to replicate some of the quiescent extracellular environments around cells, or in this case, the quiescent environment of the medium, you can achieve the same that you had seen in space. So hopefully that answered the question, but I'll be happy to expand further if not.
Thank you, Riz. And we have another question. 미세중력에서 제조된 의약품이 환자에게 투여되기 전에 철저한 품질 검사를 받아야 하는데요. 지금까지 식품의약국 FDA와 어느 정도까지 논의가 진행되었으며 앞으로 이러한 규제에 관련된 논의가 어떻게 진행될지 궁금합니다. Quality control is undoubtedly critical for any pharmaceutical product manufactured in the microgravity before it can be administered to patients. May I ask to what extent discussion with the FDA have taken place so far and how such regulatory dialogues are expected to proceed moving forward?
That's a really good question. I'll try to answer briefly, and if others want to chime in, feel free. So in the case, for example, of Keytruda, there is no FDA involvement necessary for the space component, because the space component only helps you understand that protein better. Now, the FDA part comes after that, once you're back on Earth and you're replicating what you learned from space, and now you have a new formulation of the drug. Now that has to go through clinical trials, that has to go through FDA processes. The laboratories where this is manufactured, they have to be regulated because this is going to go inside a human body, all these things. So, but for the space component in those cases, it's not necessary. Another example that I did not speak about here because of limited time is stem cells and regenerative medicine. So in those cases, the long-term vision is that, yes, you will use microgravity to manufacture something that will be used on Earth. So now you're going to have to go and do scale up processes. And once we get to that point, yes, we're going to need to have regulated processes, regulated payload facilities, because same as before, the product of that process would be something that would go to a human body. So yes, you need to have the appropriate regulations and processes implemented there. In the cases that I talked about today, did not apply because of what I explained here.
Okay, thank you for the answer. We have three more questions. One is, what is planned lifetime of Starlab space station before it is retired? 스타랩 우주정거장이 수명은 어떻게 되는지 궁금합니다. Anybody who's going to answer this?
Yes, I think I can take that one. So yes, the Starlab space station, as we look at the life cycle of our station, we see the analogous of ISS. ISS lasted for 30 years, or is going to last on 30 years before its full retirement. We expect very similar with Starlab. We do understand, though, that over that life cycle of the station, we will be looking at upgrades as well as increasing and adding modules because things degrade on orbit due to radiation. But we will be looking at how do we expand that over time throughout its life cycle to ensure that it maintains its capabilities. But the structural and the maintained and the integrity and everything else for on orbit is 30 years.
So 30 years, okay. And we have another question. You said Starlab will replace the ISS, and it has totally commercial purposes. What ground do you use the LEO? 스타랩이 이제 ISS 국제우주정거장을 대체할 것이며 상업적 목적으로 운영될 것이라고 말씀을 하셨는데요. 지구 적외도 리오를 어떤 목적으로 사용할 계획이신지 궁금합니다. Who's gonna answer that?
It's not clear in English, is it, Brad? I don't think it's clear.
Yeah, I mean, I could take a stab at it. So,
Okay.
I mean, as we think about, the Starlab will replace the ISS, but it's a commercial space station. But at the same time, we are understanding that we are working with all of the agencies in those countries to continue their research and their partnerships with industry. When we think about a commercial station versus a government-owned ISS, right? The ISS is owned by national governments. It's considered a national laboratory in space. Therefore, it has different constraints when we think about intellectual property rights, has different constraints when we think about the ability to protect people's research. They have to publish, they have to, provide, because they're getting funding and execution from NASA or ESA, JAXA, and others. So with a commercial station, we can provide that of more of a commercial type of hosting where it protects the IP of researchers. It'll help expand that level of research that goes on in space. And it provides ability to do things that you normally wouldn't do, having to go through all the bureaucracy and government checks. We still will have a very safe and robust space station that provides capability, but we need to make sure that we also can host and develop out, not under the government bureaucracy and regulations.
Okay, there's those questions are coming up. And the next question it will be mine. Could you please mention the link again, where I can watch the video, this recorded video of this workshop. 이것은 스페이스 레이더 유튜브 채널을 통해서 다시 보실 수 있고요. 현재 이 녹화되고 있는 워크숍 콘텐츠는 조만간 스페이스 레이더 유튜브 채널에 올라갈 겁니다. 그래서 그것을 참고하셔서, 물론 스페이스 레이더 웹사이트에도 제가 링크를 올릴 거고요. 그렇게 보시면 될 겁니다. The recorded video, the link to the recorded workshop will be posted on the Space Radar website, and also it's a YouTube channel. So please remind that it will be posted soon. So next question. Aside from Merck, which other major pharmaceutical company have shown interest in microgravity-based research and development? Additionally, may I ask to what extent these companies are currently in close communication or collaboration with the Voyager?
So Luis, do you want to take first part and I'll take the second?
Yeah, sounds great. The other example I showed today was Amgen with denosumab. There's other companies that are looking into cardiomyopathies, muscle dystrophies. The list is actually pretty long, and I would not want to give it partially and leave some others outside of it. So I think if you go to the ISS NL website, that is ISS as an International Space Station and NL for National Lab. On their website, they do have pretty good summaries on who has flown what. So whomever was interested in that question, I think you'll be able to find a more comprehensive answer there.
And as for the extent of companies in close communication with us, we're not going to disclose the list here, but we are in close communication with a variety of companies across the world, in pretty much every region of the world, interested in performing and continuing their experiments or things that they've already done or things they're interested in doing. And we're assisting in those developments, those discoveries, and working with a variety of different implementation and channel partners to make that happen.
Okay. Next question is, microgravity provides a huge benefit in the pharma businesses. How much impact do you expect to traditional industry? Does it mean the traditional pharma industry should be transformed totally to microgravity approach?
Yeah, good question. I don't think totally, but this is a game changer. I think just as we were able to sequence genomes, and then once we understood the structure of DNA, we were able to understand functions of different parts of the DNA. And once we understood that, we were able to learn about how diseases worked, why they started. And once we knew that, we were able to start formulating new types of medicines. I think microgravity is a similar enabler and game changer. It is not going to be something that changes everything, and now all pharmaceutical processes have to change. Absolutely not. This is a new tool that is going to enable us to really get into the 21st century and expand the ability to improve people's health and well-being.
Okay, the next question is, as Starlab plans to support biological experiments in microgravity, how does the company approach regulatory issues surrounding the international transfer of biological materials, especially across different jurisdictions? Would these regulatory frameworks pose challenges or opportunity for future collaboration with international life science partners, such as research institutions in South Korea?
I think I can chime on this, and if somebody wants to chime in later. This is no different, I think, from if you were collaborating with another laboratory in the United States. And I say the United States because really what matters in this regard is where is the rocket launching from, the rocket that has got the vehicle that is bringing that biology to space and back. So in that regard is similarly to if you were collaborating with a lab in the US, there are processes, regulations that you need to follow to make sure that those cells are coming to the country properly. That still applies. That's no different.
But I think
Okay.
I can intervene a little bit more about this because I joined the meeting for the US and the South Korea, the collaboration development. The meeting was yesterday in Washington, D.C. I was the part of the meeting. 저기 한국말로 하겠습니다. In Korean, I'm gonna speak in Korean. 그 실은 저희 회사도 이러한 레귤레이션이 주리스티컬 뭐 이런 그 어크로스 이게 보더 넘어가는 뭐 이런 부분들이 저희한테도 지금 문제가 되기 때문에 그래서 저희가 이런 부분에 상당히 지금 그 빠르게 대응을 하려고 실은 이번 미팅에서도 많은 질문들 답변들이 오고 가고 있고 실은 이런 부분들이 아직 클리어된 상황들 아니고요. 어제 미팅에 참석했던 분 중에 한 분은 그 디파트먼트 오브 커머스의 그 스페이스 커머스 관련해서 담당하는 분이 그분이 참석을 해서 지금 많은 논의들이 진행이 돼가고 있고 이런 부분들을 클리어하기 위해서 준비를 하고 있다는 정도까지만 저기 답변을 들었습니다. 제가 생각하기에는 아직도 이런 부분들이 클리어되지 않은 것으로 확인되고 있고 예, 앞으로도 많은 그런 논의들이 국가 간에 일어나야 되지 않을까 생각을 하고 있습니다.
Yeah, we have 3 more questions. I think because we have a time is limited, because I think it's better to share people with the email address where people with the question can send the email to get answer from the Voyager. We have 3 more questions. This one is, I understand that Starlab has received the largest amount of NASA funding among the 4 commercial space station projects. Does this imply that a higher likelihood that NASA-led experiment will be conducted aboard the Starlab station? I'm also curious to know if there are currently any such experiments planned.
Absolutely. So yes, I can answer this one. So as we think about, yes, we were the highest funding recipient by NASA, but I will by no means speak for NASA where they select to place their experiments. As they go forward, they're still working on, that transition phase. They're still very focused on ISS until it retires. And we'll start to see that phase in as far as the move from ISS and starting to backlog those CLDs so there's no break in research. That being said, we do understand that we are the largest and most capable space station that ever will be put up in one launch. We're going to have a full laboratory capability that can sustain and transfer NASA's science from one to the next. So we see that as a very good indication and likelihood of high utilization by all the national space agencies across the board. As far as experiments going up today, between our partners, Airbus, they have functions on the ISS. Voyager Technologies continually sends experiments to space. That is the entire business model around their exploration division, is to continue to work with NASA and others, sending payloads to space. So right now we are continually, on almost every cargo mission that goes up, we have something on board and going through. So if there's interest in doing something in the near term, we can help you facilitate that through Voyager Technologies, who also can be an implementation partner onto Starlab and transition partner onto Starlab as well. So there's a variety of levels here that we can support you today.
Great. Thanks, everyone. Unfortunately, the time for our seminar is up. There are a few existing questions, but we can continue the conversation by emailing the one on the slide, or also post it in the chat. And for closing remarks, I'll pass it to Jeffrey.manber.
Yeah, thank you, Manway. And let me say, Brad and Louise, there's some more great questions as well, Hang Soon. Maybe you can just answer them in the Q&A right now. If you go into there, it's possible to respond to the questions. So thank you, everybody. It falls to me to say thank you to the panelists, to everybody at Starlab, to Hang Soon Yoon for joining us and being such a great partner to both Voyager and Starlab. I think it's very important to show that the link that can exist between Starlab, Voyager today on the International Space Station, and South Korean industry. And Hang Soon, you did that beautifully. So thank you very much for your presentation. And let me say, Sisu, thank you so much for contributing the time, your publication, Space Radar. We appreciate it very much at Starlab and Voyager, your help in making this workshop a reality. And so thank you. Manway Chen, thank you so much for your contributions as well. So with that, we will close the workshop. Any further questions, please reach out to myself or anyone on our team. And we look forward to visiting with all of you in person in Korea over the next couple of months. So thank you to everybody. And it's all appreciated, the time that's been put into this. Thank you.
Thank you very much. 감사합니다.
감사합니다. 오늘 모두 바쁜 시간 와주셔서 감사합니다. 오늘 워크숍 이것으로 마치겠습니다. 감사합니다. Thank you very much.
Okay. Thank you.
감사합니다.
예.